Hey everyone, welcome to Venus Neuron, your go-to source for medical school success. Now in this video, we're going to talk about periodic table, quantum number, and break everything about the basics of chemistry. Now let's get started. So what is periodic table? Periodic table consists of 118 elements in 18 groups, which are those vertical lines that you see, and 7 periods, which are the horizontal ones, okay? The horizontal rows are called period. Now, elements in periodic table are organized by increasing atomic number. So what is atomic number? So atomic number in chemistry is the number of protons in the nucleus of an atom. It is denoted by the symbol Z and determines the identity of an element. For example, hydrogen, or H, has an atomic number of 1, meaning it has 1 proton. Or, on the other hand, we have oxygen with O. It has an atomic number of 8, meaning it has 8 protons. Since atoms are electrically neutral, the atomic number also tells us the number of electrons in a neutral atom. The atomic number is unique to each element and is used to arrange elements in the periodic table. Now, in this table, we know that we have some groups that have special names based on their specific properties. For example, group 1 is called alkali metals, group 2 are called alkali earth metals, group 3 to 12 are transition metals, or in another hand, the D block. We're going to explain what they are. Group 7 are halogens, and group 8 are noble gases. So what is an alkali metal? Alkali metals are the elements in group 1 of periodic table, well, except hydrogen. They are highly reactive metals with 1 electron in their outermost shell, which is also called valence shell. Now, what are their properties? They are highly reactive, especially with water, forming hydroxide and hydrogen gas. Soft metals can be cut with a knife. So another property is being soft metals. They also have low density. Some, like lithium, can float on water. They have low melting and boiling points compared to other metals. And they are also good conductors of heat and electricity. So what are the examples? We have lithium, sodium, potassium, rubidium, cesium, and francium. Their atomic number is 3, 11, 19, 37, 55, and 87. Well, about francium, it's rare and highly radioactive. Now, because of their high reactivity at the alkali metals, they are usually stored in oil to prevent them from reacting with moisture or oxygen in the air. Now, let's move on to alkaline earth metals. They are elements in group 2 of the periodic table, and they are slightly less reactive than alkali metals, but still highly reactive. Now, what are their properties? They have 2 electrons in their outermost shell. They are reactive, but less so than alkali metals. They are harder and denser than them. They have higher melting and boiling points compared to alkali metals, and form basic or alkaline oxides and hydroxide when reacting with water. They are also good conductors of electricity and heat. Now, what are the examples of them? We have beryllium, magnesium, calcium, strontium, barium, and radium. And you need to know that radium is radioactive, okay? These metals are commonly found in minerals in the Earth's crust, hence the name alkaline earth metals. For example, calcium is found in limestone and bones, while magnesium is in chlorophyll, the green pigment in plants. Now moving on to transition metals, which are the elements found in groups 3 to 12 of the periodic table. They are known for their variable oxidation states, metallic properties, and ability to form colored compounds. Now let's talk about their properties. They have high melting and boiling points. They are good conductors of heat and electricity. They are malleable and ductile, meaning that they can be shaped and stretched. They have variable oxidation states, means that they can form multiple types of ions. They form colored compounds, and they often act as catalysts in chemical reactions. We're going to talk about it in future videos, okay? Don't worry about it. Now, what are the examples of transition metals? We have iron, copper, zinc, silver, gold, and platinum. Now, what are they used for? For example, iron is used in construction and steel production, or copper is used in electrical wiring and plumbing, or gold and silver are used in jewelry and electronics, and platinum is used in catalytic converters for cars. So basically, transition metals play a crucial role in industry, technology, and biological systems. For example, hemoglobin in blood contains iron. One more group to go. We have halogens, which are elements in group 17 or main 7th group of the periodic table. They are highly reactive nonmetals that readily form compounds, especially salts with metals. The name halogen means salt former because they commonly form salts like sodium chloride or table salt. Now, what are their properties? They have 7 valence electrons, so 1 electron short of a full outer shell. You know, we have 8, right? We have 8 electrons when the outer shell is full, okay? So this one has 1 less. They are highly reactive, especially with alkali metals and alkaline earth metals. They exist in different physical states at room temperature. For example, fluorine is gas, or chlorine is gas. We have bromine, which is liquid at room temperature, or iodine, which is solid, and acetone, which is also solid, and it's rare and radioactive. They form diatomic molecules. We have F2, Cl2, and so on. They are toxic and corrosive in pure form. Okay. So the examples of halogen, as I said in the examples, are fluorine, chlorine, bromine, iodine, and acetone. Now, what are they used for? So, for example, fluorine is used in toothpaste in the form of fluoride and Teflon coatings. Or chlorine is used in disinfectants, bleach, and swimming pools. Or bromine is used in flame retardants and pharmaceuticals. Or iodine is used as an antiseptic and in thyroid health. So because of their high reactivity, halogens are rarely found in their pure elemental form in nature. Now, noble gases, which is the last group we're going to talk about, are the elements in group 18 of the periodic table. They are known for being chemically inert, means unreactive, due to their full outer electron shells. This stability makes them different from other elements. Now, what are their properties? They have full valence shell, meaning 8 electrons, except helium, which has only 2, okay? They have very low reactivity, or some say none, and they so rarely form any compounds. So you need to go and check your reference book to see which one is going according to your curriculum. If they consider it as nothing, like no reactivity, or very low. They are colorless, odorless, and tasteless gases at room temperature. They have low boiling and melting points. They are non-flammable and non-toxic, except in extreme conditions. Now, what are the examples of noble gases? We have helium, neon, argon, krypton, xenon, and radon. And radon is radioactive. Now, what are they used for? For example, helium is used in balloons, airships, and cooling superconductors. Or neon is used in neon signs and high voltage indicators. Or argon is used in light bulbs and welding to prevent oxidation. Or krypton and xenon are used in specialized lighting and lasers. Or radon is used in some cancer treatments, though it is radioactive and hazardous. Since noble gases are very stable, they do not readily react with other elements, which makes them useful in many applications where chemical reactivity is undesirable. Now let's move on to the fun part. We have some periodic properties in periodic table, such as atomic radius, ionization energy, electronegativity, and electron affinity. So what is atomic radius? It shows the size of the atom, hence the name. Atomic size depends on number of shells and effective nuclear charge. In one group from up to down, atomic size increases because number of shells is increasing. Now let me give you a little information if you're still confused about it. A period is a horizontal row in the periodic table, and as I said, we have 7 periods in total. Now in each period, electron shells increase, so moving left to right, elements gain 1 more electron in their outer shell. The number of electron shells or energy levels stays the same within a period. For example, period 2 elements, lithium, beryllium, boron, carbon, and etc., they all have 2 electron shells, okay? Also, their atomic number increases, so each element has 1 more proton than the previous element. Their reactivity changes, okay? So metals on the left side become less reactive across a period, or nonmetals on the right side become more reactive until group 17, or halogens. And noble gases, or group 18, are inert, or non-reactive, okay? Or their metallic character decreases. For example, elements on the left are metals, sodium, magnesium, and so on, and elements on the right side are nonmetals, such as oxygen and fluorine, okay? Ionization energy and electronegativity is going to increase, but we're going to talk about it in a few minutes. Now, what happens in each group? So a group is a vertical column, as I said, in the periodic table, and we have 18 groups. But they have same number of valence electrons. So elements in the same group have the same number of valence electrons, which determines their chemical behavior. For example, in group 1, or alkali metals, they all have 1 valence electron, such as lithium, sodium, potassium, and so on. We also have reactivity trend, which means, for example, metals on the left side, their reactivity increases going down the group. Meaning, for example, potassium is more reactive than lithium. Or nonmetals on the right side, their reactivity decreases going down. For example, fluorine is more reactive than iodine, okay? Their atomic side increases down the group. As new electron shells are added, atoms become larger, okay? So in conclusion, periods or rows show trends in energy level, size, reactivity, and ionization energy across elements, and groups or columns show similar chemical properties due to the same number of valence electrons. Now you might wonder, what is a valence electron? It is an electron in the outermost shell or energy level of an atom. These electrons determine how an element reacts chemically with other elements. They are involved in chemical bonding. For example, elements react by gaining, losing, or sharing valence electrons to achieve a stable electron configuration, usually 8 electrons, which is known as octet rule. They also determine reactivity. For example, metals like sodium tend to lose valence electrons to form positive ions, or nonmetals like oxygen tend to gain valence electrons to form negative ions. Or noble gases like helium or neon have full valence shells and are unreactive. And if they're in the same group, they have same valence electrons. So same group is equal to same valence electron. So elements in the same group or column of the periodic table have the same number of valence electrons and similar chemical properties. For example, group 1 or alkali metals all have 1 valence electron. Okay? Now, let's talk about valence electrons in sodium as an example. So sodium, or indicated with Na, has 11 electrons. Okay, guys, the elements in the periodic table are either shown by one letter or two letters, which if it's one letter, that's capital letter, and if they're two letters, the first one is capital, okay? Don't mix them up. The electron configuration of it is 281, and the last electron, which is the one that I said 1, it's the valence electron, which is in the outermost shell. Now, sodium, it loses like 1 electron to become sodium ion for stability. So why are they important? As a conclusion, they determine how elements interact to form molecules and compounds. They explain trends in the periodic table, such as reactivity, bonding types, and electrical conductivity. Okay? Now, going back to atomic radius. So we said that it shows the size of atom, and atomic size depends on number of shells and effective nuclear charge. In group from up to down, atomic size increases because number of shells is increasing. Now, in a period from left to right, it decreases because number of shell is constant, but number of electron is increasing. Now let me break this one down. What is nuclear charge when I talk about it? Nuclear charge is the total positive charge of the nucleus of an atom. It is equal to the number of protons, or basically called atomic number, indicated with letter Z, in the nucleus because each proton carries a 1 positive charge. Okay? So nuclear charge is number of protons and indicated with capital letter Z. For example, hydrogen has 1 proton, so its nuclear charge is positive 1. Or oxygen has 8 protons, so its nuclear charge is positive 8. Or calcium has 20 protons, so its nuclear charge is positive 20. Okay? Now, another thing that I said about atomic radius decreasing across a period. So the reason is we're first increasing nuclear charge because as you move across a period, the number of protons in the nucleus increases, so the nuclear charge increases. And this higher positive charge pulls the electrons closer to the nucleus, reducing the atomic size, okay? We also have constant electron shells. So all elements in the same period have the same number of energy levels or shells. And since no new energy levels are added, so increased nuclear charge pulls the existing electrons tighter towards the nucleus. We also have increased effective nuclear charge. Electrons in the inner shell shield the outer electrons from the full nuclear charge, which is called shielding effect. However, shielding remains nearly constant across a period while the nuclear charge increases. This results in a stronger attraction on the valence electrons, pulling them inward and reducing atomic size. We also have stronger electron nucleus attraction. Since valence electrons are being added to the same shell, they experience a stronger pull from the nucleus. This shrinks the atomic radius as you move from left to right across a period. Okay? So let me give you a conclusion on it. So across a period from left to right, atomic radius decreases because more protons means a stronger nuclear attraction, same number of energy levels, meaning no extra shielding, and electrons are pulled closer, shrinking the atom. Okay. Now let's talk about another trend or another periodic property of the periodic table. We have ionization energy. It is the energy required to completely remove an electron from an atom in gaseous state. In a group from up to down, ionization energy is decreasing. And in a period from left to right, it increases because the attraction force from nucleus is increasing. Now let's go a little more into detail. So ionization energy, or IE, sometimes people write it this way, is the energy required to remove an electron from an atom in its gaseous phase. When an electron is removed, the atom becomes a positively charged ion, okay? So there are two important concepts related to it. First, ionization energy, it is the energy needed to remove the first electron from an atom. We also have second ionization energy, which is the energy needed to remove the second electron after the first has been removed. Okay, hence the name. This is usually greater than the first one because the ion formed after the first removal is more positively charged, so it holds the remaining electrons more tightly. Okay, now what are the factors that affect it? Nuclear charge is one of them. The more protons in the nucleus, the stronger the attraction between the nucleus and the electrons. If we have higher nuclear charge, it means higher ionization energy because it requires more energy to overcome this attraction. Another factor is distance from the nucleus or atomic radius. Electrons that are farther away from the nucleus are less tightly held because the attraction decreases with distance. Or if we have larger atomic radius, it means lower ionization energy because it's easier to remove an electron that is farther away. Another factor is shielding effect. Electrons in inner shells can shield outer electrons from the full pull of the nucleus. If we have more shielding, it means lower ionization energy because the outer electrons are more easily removed due to reduced nuclear attraction. And the last factor is electron configuration. Atoms with a stable electron configuration, like noble gases, require more energy to remove an electron. For example, removing an electron from a noble gas, which has a full outer shell, takes a lot of energy because they are highly stable. Now we said that across a period, from left to right, it increases. So, basically it could be because of increasing nuclear charge, meaning we have more protons that pull the electrons more strongly. It's also because of decreasing atomic radius, so the electrons are held tighter to the nucleus, making it harder to remove them. And it's also because shielding remains constant across a period because electrons are being added to the same energy level. Now, what happens down a group from top to bottom? Ionization energy decreases as you move down a group. So why? Because of increasing atomic size, meaning more electron shells. It means the outer electrons are farther from the nucleus and experience less attraction. We also have increased shielding from inner electron shells, reduces the effective nuclear charge felt by the outer electrons, making it easier to remove them. Okay? Now, there are some exceptions. So while ionization energy generally increases across a period and decreases down a group, there are a few notable exceptions. For example, in groups 2 to 13, we have, for example, beryllium, which its ionization energy is 899. We have boron, which its ionization energy is 800. So why the decrease in ionization energy? Boron, or indicated with capital B, has an electron in the 2p orbital. The 2p orbital is slightly higher in energy than the 2s orbital, so it is easier to remove an electron from boron than from beryllium, which has a full 2s orbital. Okay? We're going to talk about orbitals, don't worry. Or another thing, we have groups 15 to 16. We have nitrogen, which its ionization energy is 1402, and we have oxygen, which its ionization energy is 1314. So why the decrease in ionization energy? Because oxygen has a paired electron in its 2p orbital, creating more electron-electron repulsion. This makes it slightly easier to remove the electron compared to nitrogen, where the electrons in the 2p orbitals are unpaired. Now let's talk about the third trend in the periodic table. It is electronegativity, which is the ability or measuring the attraction of an atom for the electrons in a chemical bond. So it means how atoms want to hug or share or gain an electron. In a group from up to down, it decreases, and in a period from right to left, it increases. Okay? Now let me explain it in another way. It is basically a measure of an atom's ability to attract and hold on to electrons when it forms a chemical bond with another atom. The higher the electronegativity, the more strongly the atom will attract electrons toward itself in a bond. Electronegativity is a relative scale, meaning it is compared to other elements. The most commonly used scale is the Pauling scale, named after Linus Pauling, where fluorine is the most electronegative element with a value of 4. Okay, you need to know this number, which is 4. Now, what are the factors that affect it? We have nuclear charge. The more protons, meaning higher nuclear charge in the nucleus, the greater the ability to attract electrons. So elements with more protons tend to have higher electronegativity. Another one is atomic radius or size. The smaller the atomic radius, the closer the electrons are to the nucleus, leading to stronger attraction. Therefore, smaller atoms tend to have higher electronegativity because their nucleus can more strongly attract bonding electrons. And the last factor is shielding effect. Electron shielding occurs when inner electrons reduce the nuclear pull on the outer electrons. Atoms with more electron shells, which means, well, bigger atoms, experience more shielding, reducing their ability to attract electrons, thus lowering their electronegativity. Okay? So as I said, from left to right in a period, it increases. So why? Well, because nuclear charge increases, so it means they pull electrons more strongly. And the other reason is that the atomic radius decreases, bringing the bonding electrons closer to the nucleus, which enhances attraction. Okay, so for example, we have sodium, its electronegativity is 0.93, and chlorine, which is 3.16. So as you move from sodium to chlorine, electronegativity increases. And as I said, down a group, it decreases. So why? Because the atomic radius increases. Do you know what that means? Right, more electron shells. So the bonding electrons are farther away from the nucleus. And there is also more shielding from inner electrons, making it harder for the nucleus to attract bonding electrons. As an example, we have fluorine and iodine. For fluorine, the electronegativity is... Correct, it's 4. And for iodine, it's 2.66. So as you move from fluorine to iodine, it decreases. Okay. Electronegativity plays a key role in determining the type of bond that will form between atoms. For example, if we have nonpolar covalent bond, it means that their electronegativity difference is approximately 0. So they will share electrons equally, forming a nonpolar covalent bond. For example, two identical atoms like hydrogen or chlorine, they have the same electronegativity, so the electrons are shared equally. Or we can have polar covalent bond, which their electronegativity difference is 0.1 to 1.7. If the electronegativity difference is moderate, one atom will attract the electrons more strongly, creating a partial negative charge, shown like this, on the more electronegative atom, and a partial positive charge, shown like this, on the less electronegative atom. For example, in water, oxygen is more electronegative than hydrogen. So the electrons are pulled more towards oxygen, making it partially negative. Or lastly, we can have ionic bond, in which the electronegativity difference is more than 1.7. So if it's large, one atom will completely take an electron from the other, forming ions. This results in an ionic bond. For example, in sodium chloride, sodium donates an electron to chlorine, forming sodium ion and chloride. Okay? Now, you might want to know the lowest electronegativity value, which is for francium, and it's 0.7. Okay. The last trend that we're going to talk about today is electron affinity. It reflects the ability of an atom to accept an electron. It is added to a gaseous atom, okay? So it's like basically how much they want electrons. In a group from up to down, it will decrease, and in a period from left to right, it increases, okay? Now let's go into more details, or explain it in another way. Electron affinity is the energy change that occurs when an electron is added to a neutral atom in the gas phase to form a negative ion. It is a measure of an atom's tendency to accept an electron, okay? So if energy is released when an electron is added, the electron affinity is negative. If energy is required to add an electron affinity is positive, which is rare, okay? So why is it important? It indicates how strongly an atom wants to gain electrons. Atoms with a high electron affinity are more likely to gain electrons and form negative ions, or called anions. It is closely related to the reactivity on nonmetals, especially halogens, which tend to gain electrons easily. Now, what about its trends? Across a period from left to right, it becomes more negative, meaning more energy is released as you move from left to right across a period. So, why is that? As you move across a period, atoms have more protons, which increases their nuclear charge and thus their ability to attract and hold electrons. The atomic radius decreases, so the added electron is more easily pulled towards the nucleus, releasing more energy. Okay, now down a group from top to bottom, it becomes less negative, so less energy is released as you move down a group. So why is that? As you move down a group, the atomic size increases, so the added electron is farther from the nucleus, so the attraction between the electron and nucleus is weaker. We also have more electron shielding from inner shells, which also reduces the nucleus' ability to attract the incoming electron, making the process less exothermic. Okay, so let me talk about the key points and a summary about it. Electron affinity is typically negative for most nonmetals, meaning that energy is released when they gain electrons. Noble gases or group 18 have very low or even positive electron affinities because they already have a full valence shell, so they are reluctant to gain electrons. For example, neon has a very small or slightly positive electron affinity. Or halogens or group 17 have highly negative electron affinities, which is why they are so reactive and readily gain electrons to form anions, such as chloride ion. So let me give you a summary on it. Electron affinity is the energy change when an electron is added to an atom. Across a period from left to right, it is more negative, meaning it increases. And down a group, meaning from top to bottom, it is less negative, meaning it basically decreases. The reason for decreasing from in a group from top to down is because of increase in atomic size and shielding effects. And for a period from left to right, it's because of higher nuclear charge and smaller atomic radius. Okay, so let's sum up everything we've said so far. Atomic radius within a group, it increases. Within a period, it decreases. Ionization energy within a group decreases and within a period increases. Electronegativity within a group decreases and within a period increases. Okay? Now that was all for today's video, and in the next video we're going to talk about atomic orbitals and electrons that are described by quantum numbers, and we'll go through types of primary bonds. Okay? And as always, stay curious, keep learning, and I'll see you in the next video.